Hello and welcome to this virtual webinar. Our topic today is establishing requirements, extracting metrics, and evaluating the quality of LiDAR data. I'm Mike Cook, the lead applications engineer over at TopoDOT. I've been here for 10 plus years and I've got medals to prove it. And I work with the support, development, and sales teams. I am not alone. We have a dedicated team. We're based out of sunny Orlando, Florida, and we're basically here to help support the TopoDOT community. We're a software development company, but we also provide training, support, and consulting services. TopoDOT is an industry-leading software application for extracting high-quality topographies, 3D models, and assets from point cloud data, which feeds downstream operations across multiple disciplines. The primary application areas for TopoDOT include the following: transportation corridors, both rail and roadway, electric and power corridors for transmission, distribution, and substations, as well as bridges, tunnels, and general structures. Our focus today will revolve around strategies for assessing data quality. All right, let's get into our agenda for today. I've already given a brief introduction, but I'll dive into three main topics. What's LiDAR, and what are some of the origins of uncertainty? How to establish these data requirements, and a practical look at how this can impact your productivity. The objective here is to make you an expert in data assessment to help answer the question of whether or not your data meets the requirements for your application. Let's get started. What is LiDAR? LiDAR, light detection and ranging, is a remote sensing method used to examine the surface of the Earth, according to NOAA. It uses light in the form of a pulsed laser to measure ranges, or variable distances, to an object. These light pulses, combined with other data recorded by the system, generate precise three-dimensional information about the shape of its surroundings. In this example, we have a mobile LiDAR system, MLS in short, that is traveling down a highway corridor, performing multiple passes. This occurs at highway speeds and is collecting millions of spatial points along with high-resolution photos. Alongside the road, the survey crew is installing and locating control targets for the system to identify. These targets tie down the data for a resulting high accuracy and high precision product. Information can then be pulled or extracted to produce an HD map or topography. Its applications run wide. Here are a few: corridor mapping and or HD mapping within road and rail, as well as tunnels, pipelines, and power lines. Asset inventory, 3D modeling, analysis, such as clash detection and simulation, measurements for ADA compliancy, pavement condition reports, clearances, cross slopes, grades, and many more. And there are a lot of options on the market. Here's a handful of mobile LiDAR systems, and they all produce data with a variety of data characteristics between them. But what they collect and how they collect usually remains the same. And it's going to be producing these common components, which are going to be collected and used. We have point cloud data, calibrated images, which are very useful and important, and then the survey control. This is what the system's going to use to locate itself. Let's first understand how a scanner fundamentally works. The majority of scans out there rely on time of flight approach. A beam goes out and it comes back. And it's done in a short period of time, allowing it to calculate the distance. Common scanner rates are 500,000 points per second and more. That's a lot of points. Now, if we look at a small cluster of points or a sample on a flat wall, we'll see two types of uncertainty: random and systematic error. Random error is the fuzziness of the data, because there's going to be a certain amount of plus or minuses to the precision of that instrument. And a bunch of plus and minuses leads to a fuzzy or a thickness of data. For systematic error, this is the shift in the data. The average of the data can be shifted from the actual wall. So if we're looking for a flat surface, we can imagine or visualize fitting a line down the center of the data cluster. That's going to be slightly shifted from where the actual wall is. This could be due to a few things: registration mistakes, wrong temperature and pressure settings, reflectivity issues, the distance to the wall, or even the incident angle of beam. Here's a few examples of uncertainty, specifically for static systems. Vibration is going to be a random noise, so you might have nearby heavy equipment that can oscillate the platform. It could be on a tripod or it could be on a lift like this. For control targets, the error there would be systematic. Okay, if there's something wrong with the target, then everything using this target will be affected. Some scanners rely on these targets to orient themselves via a resection method. Others use common surfaces between multiple scan positions. So any tilting, vertical, and horizontal shifts can creep in to these types of data sets based off the control being not plumb or positioned incorrectly. How about a mobile platform? It's a more complex system, and it's moving. These systems mainly see systematic error. A few sources of error include the platform system vibration, which is going to be random. Maybe the IMU can't compensate if it's not fast enough to control or dampen out those vibrations. Sensor misalignment, which would be systematic. So this is more of like a fixed error. Trajectory error, again, systematic. It's not always perfect, and there's going to be plus and minuses. And then there's going to be the control target alignment, which again is another systematic error, similar to what we saw previously. The data has got to be tied into some control. And if the control's wrong, or it's matching improperly, you'll have that error. So there's a lot to worry about. And most of us don't need to worry about anything or everything involved with the system. We just want the data to be delivered based off of specified requirements, which can be measured, and we'll soon define that. We'll break this down into 6 attributes that characterize the data. And these can all be measured to produce data metrics. And keep in mind, this is a quick summary of TechNote 1021, which can be found on our website. It's a 40-plus page white paper, and it goes into detail on the concepts involved, including those sources of uncertainty. But today I'm providing a brief outline on the topic within this presentation. What we'll see is that every aspect of your point cloud can be reduced to a parameter, 12 parameters to be exact, which gives the recipient the power to set requirements. And surveyors are as important as ever right now, especially for LiDAR technology. The accuracy of the control network is basically the foundation of most LiDAR data collected out there. Our first characteristic is survey control alignment, or how well does the data line up to control. This is done by comparing control points against this local point cloud sample. What's measured is the deviation in the vertical and or horizontal. So control can be found on horizontal and vertical surfaces. They can be in the form of targets or visible features, such as the intersection of paint markings. For mobile projects, you'll typically see chevron targets spaced every 500 to 1,000 feet. These targets will appear in the point cloud data itself, allowing for this type of evaluation. The resulting report will provide deltas for X, Y, and Z for every control point. What about the data between the control? How is that checked? This leads into the next type of measurement, and this characteristic will be the scan-to-scan alignment. In the cross-section of the barrier, we may have 4 to 6 scans overlapping each other, represented in different colors here. On the left side of the barrier, we have red and blue, and on the right side, we have green and yellow. So those are going to represent our different scans. We want this data to line up here, just like it is. So we're measuring the separation between one scan file and another to get a colorized heat map. Vertical alignment checks are easy because it's an automated process. And then horizontal alignments will be done through cross-sections on identifiable features with overlap, such as this barrier, poles, building corners, edges, and other objects. And again, same characteristic here, but with more separation. On the right, this is what you'll actually generate when running the evaluation. An image is generated with each pixel being a data measurement point, and essentially a color gradient is applied to every pixel here according to the deviation range that's defined by the user. So cyan in this case is good, magenta is bad, and the range here is about 1/10. And the entire world is a control here, because we can measure what's happening in between the control. And always ask for multiple passes as a requirement in order to perform a test like this. The reason being is mobile data does not make the same mistake in the same place at different times. Our third characteristic is the alignment of calibrated imagery. A simple question can be asked: how lined up is the image to the data? The idea here is to measure the pixel shift from an identifiable feature, such as an edge of pavement, edge of stripe, barrier, or a corner. And we can put a requirement on this, expecting images to be within 5 to 10 pixels, and then if anything's over that, it's a little sloppy. But at least you could put that requirement on that picture. So we have now established lineage between our system data and the control survey, and we have the tools to do it. Note that the survey points or the control are the only sealed document, and everything else is tied to this. So there's nobody sealing the actual point cloud, and nobody's saying that the data is correct, because the survey points are the only legal binding set of points for this point cloud. And it's important to provide this traceable path for the data back to control. All the data should be tied down to this control, which is key. Okay, let's continue on with some more. Let's set up some random noise requirements. This can be measured by taking a thin cross-section across the curb or something that's flat. And then you just simply measure it. You just measure peak to peak of the fuzz or the top and bottom points to determine the noise. Typically, you'd want random noise to be about 1/4 of the smallest feature you want to identify. And that could be taken as a rule of thumb. But for example, if you're looking to identify a curve profile, then your noise thickness should not exceed, let's say, 1/10 of a foot. Our fifth characteristic is point densities, specifically horizontal densities, or how many points within a defined area. Here we have an example of the evaluation done in TopoDOT on static data. You can see the individual positions as green patches. Static densities are usually very high right around the scanner. However, it drops off as you move away from the source. So on the left-hand side, we can see the analysis showing about 21 points per square foot, and this is in between the scan positions. So the scanners are spaced properly here. We want to shoot for about 20 points per square foot. On the right, we could see 2 points per square foot, so that means the scanners are just too far apart. It's not providing enough detail in between the positions. And remember, we're in the world of topography, so we're not looking for bolt patterns on structures or anything like that. If you are, you're going to need more points than what we're saying here. Here we're looking for curbs, barriers, breaks, etc. So these densities apply to the outside world of topographies for corridor projects. For mobile and static data collects, again, we want to see more than or at least 20 points per square foot in order to see profiles. For airborne data, not so much. They might see like 5 points per square foot, but in order to get higher than that, it's just going to be too expensive, which is usually the case. But with the advancements of like drones combined with smaller scanners, this is airborne data is becoming a real possibility with those like low altitude systems. Finally, last but not least, we have coverage. And we can ask how much of the field was captured or how much was not captured. In this example, we have a static project with large shadows. A laser is light, so it can't go through solid or opaque objects. This shadowing may occur from people, cars, trucks, etc. And gaps may occur from scanners being too far apart. For gaps, it's not the range of the scanner. It's really the angle that the beam strikes flat ground. And because tripods sit relatively low, this can limit the range down to about 150 feet on flat ground. So it's a very common problem. We see this a lot, and improving the scanner resolution won't help either. You can always raise the scanner, so if you double the height, you'll double the horizontal range on flat ground. So what about mobile systems? Mobile systems are also susceptible to shadowing. And that's due to also people, parked cars, moving cars in this case, guardrails, steep ditches, heavy brush, etc. As well as limited range on flat ground. So a single pass can span across maybe 2 to 3 lanes, depending on the scan height. So in most cases, you'll need at least 2 passes to help improve coverage. So we're done identifying the measurable characteristics. However, we need to consider project scope and the scan platform used so that we can help place realistic requirements. Here we have a hypothetical project laid out where we have data from different times and different platforms for a variety of applications. So we've organized our tiling options to distinguish which type of data should be used in which area. So, maybe airborne quality is good enough for shoulder to boundary work on all soft terrain. Mobile is good within the paved surfaces, so shoulder to shoulder or all the hard surfaces. And static is good for complex structures like bridges, where maybe multiple setups are required for absolute coverage, and where tolerances are the tightest. Well, let's take a closer look at this bridge requirements in the green zone. Here on the bridge, static data is used to meet the demanding requirements, and we can confirm this by equating all these requirements to measured values. So within this table, we have 12 parameters to require. And these numbers are going to tell us that we have the right point cloud to do the job. And that's powerful. And to see the requirements for other platforms, such as mobile and airborne, just refer to that TechNote 1021 that I mentioned will be on our website. And consider this as a guideline for your surveying needs. It's recommended to adjust these based off of your applications. Now it's time for the speed round for practical tips. What if I don't collect photos? What if I collect only one pass of data? What if I go with a fuzzy scanner or a budget-friendly scanner? And how will all of this affect what I'm trying to do with the data? So in this section, I'd like to help answer some of those questions and how they impact extraction productivity. And I'll state extraction productivity as the ease and speed and quality of the work by the end user. Imagery is going to help identify objects within the point cloud. So if you don't have imagery, you won't be able to determine like sign type or cracks or manholes, anything that's like small that kind of gets lost between the lines of the scanner. Or you just won't be able to identify most flat objects. So as a rule of thumb, that's how images kind of come into play. How about the resolution of the photos? If you're looking to identify signs that are really small, then consider photos at a higher resolution. What's on the pole, how many signs, is there a utility riser? If you need those types of details, the higher resolution photo will supply that. For general terrain, lower resolution photos are just fine because curbs are usually large and hard to miss. How about the overall alignment of these photos? Even if the requirements are not met, these images can still be used as a reference to some extent. But at some point, severe misalignment will create its own challenges for the user. And how many cameras do I need? At what orientation? How often should these pictures be taken? Should I control the interval by distance or by a timer of when these photos are taken? Seen here is basically a forward-facing camera and a side-facing camera. So let's talk a little bit more about that. In the left image, we have 4 camera orientations. Forward and rear, and then we have left and right. And those are the fields of view there, those green lines. So when you're doing asset inventory, this setup will be key for identifying those objects. When you're only doing topography, a forward and or rear facing camera should do the trick. We can see the forward camera's field of view in the right image. Looking closer at the right image, we can see the interval or spacing between one photo and the next. So make sure this is not too far for your application, or else you'll miss features between those gaps. If they're too close, you'll end up with basically an unnecessary set of file sizes. How about the alignment of our data? So data separation in localized areas is manageable. However, an abundancy of it will cause confusion. For example, you have 2 of the same curve profiles separated by, let's say, a half a foot. Which one do you pick? Okay. The fuzzier the data, the harder it will be for the end user. They need to be able to see from top view where to apply certain automated routines, especially for hard breaks, curbs, sidewalks, edge of pavements, etc. Ground routines, though, are usually unharmed by this fuzzy data and can remain fairly automated. Here's another example of fuzzy data versus, let's call it crisp data. If you were to locate the top of a rail and maybe the cross slope or the cant of the rail, maybe the width or the gauge of the rail, just ask yourself, what data set would you prefer here? We can clearly see way more definition on the right-hand side versus the left-hand side. And every application is going to be slightly different. Densities are usually a direct link to scanner and vehicle speed, as well as the amount of passes that are conducted or the amount of scans that are gathered. If scan line gaps are too large, certain features won't be obtainable. All right, or the extraction process will become too subjective. A low density point cloud has to be complemented with imagery if it's just not supplying enough visual information. That image will kind of come into play to help fill in those gaps. Multiple passes, they're basically going to help with overall density, and it's going to help combat shadowing. And especially for like moving cars, that'll create a shadow, but the second time you scan, that car should technically not be there. And with less shadowing, you have less problems when it comes to identifying certain things. And so density in this case, the more defined a brake line is, the easier the extraction becomes. And essentially just, the more definition equals, the more automation that you can apply. So it does, in this case, boost the extraction speeds when you increase densities. And with more passes or scans, the easier it becomes to see features from top view. However, relative alignment is also key in making this work. With poor misalignment, detailed features like joint lines or this ramp will not stand out. It'll be hard for the user to identify those. Looking at intensities, having a consistent intensity value across the swath of the data is very important. Not only does this allow for more automation, but it improves the user's ability to understand, what they're looking at. In the left image, we can see clearly how the intensities stay consistent from sidewalk to sidewalk. In the right image, the intensities tend to blend together, and they're not as consistent. Remember, the intensities vary based off of distances from the scanner source. So this should be accounted for. When data lands on the opposite side of the road, it should be adjusted so that it doesn't conflict with another pass from that side. If all of your scans can agree on the intensity value of an object, you will see its benefits. Not only does it help with extraction, but it also helps with registration too. Okay, keep in mind that the target here has overlapping data from at least 3 different passes. So imagine trying to line up, all those with conflicting intensity visuals. It becomes a very difficult process. And a wider range of intensity values allows for identifying a wider range of materials or surfaces. So let's say there's a 0 to 5,000 range set of values versus a 0 to like 65,000. That's the wider range that we're talking about. So the resolution of the intensity is going to help visually display a wide variety of materials. Automation is boosted with the help of consistent values. And without intensity, extraction would be very difficult. Keep in mind, I have not mentioned RGB assignment yet. The RGB would come from imagery and, can act as an intensity substitute. But image alignment plays a role here too. You need good imagery alignment so that your RGB values are projected properly onto the point cloud. And a quick note on file formats. I just stated that intensity is a must, as we just saw. Very common format is LAS, but obviously the spatial information is there. RGB is a bonus. Point source ID information is a valuable tool. This helps you basically distinguish, one scan from another. So if you have to separate them later. And a rough classification helps clear out all the overhead data, especially when you're, just working on topography. You don't want any like trees or power lines in your line of sight. Or you can reverse this strategy here. If you're just working on distribution lines, you can actually clear out the ground while you're working on distribution lines. How about the amount of scanner count and the configuration? So do you go with a single head or a dual head scanner? And what orientation do you pick? 90 degrees, 45 degrees, 30 degrees? With only one scanner, it's more likely to pick up shadowing or have shadowing. And not only that, is the shadowing will be a larger footprint usually. This can be solved with multiple passes and possibly reorienting the scanner as you go. Because if you pick up a car in one pass, you most likely won't get it in another, especially with a single head. Now for dual head scanners, what's done in 1 or 2 passes here takes a single head scanner about 2 to 4 or even more passes depending on the scenario. An example dual head configuration is a butterfly layout. So you got one scanner on each side, and their scan planes are at a 30 to 45 degree angle to each other. And they're going to be tilted so that their planes aren't plumb. And to help kind of visualize this, just imagine the scanning planes forming 2 butterfly wings. And this dual head configuration helps reduce shadowing altogether, and or it reduces the actual footprint of the shadow itself. So in the picture on the right here, it's a semi-truck, right? While one scanner was blocked, the other one filled in. Think of it as like 2 separate spray paint cans, and they're in sync, and you just basically apply one coat, and you're getting much better coverage with those 2 scanners. And ultimately, improving the coverage is going to improve the extraction process. There's not going to be any gaps in your data set. Looking a little bit more into the orientation of the scanner, what is the best orientation? We'll look at one scanner head at the moment for this, and there's a variety of angles to pick from. But here's an example. We're going to go with 45 degree example, which we can see on the left, and then there's a 90 degree one on the right. So you got an angled versus a perpendicular one to the direction of travel. And which ones should you go with? Let's first take a look at vertical assets and how they're captured. These do seem to be affected the most when it comes to the angle. A plumb perpendicular scan plane tends to miss signs or vertical objects. Essentially the sign can slip between the scan line gaps seen in the bottom image. Whereas an angled and or tilted scan plane avoids this, giving you way more coverage of the sign. And this can be seen in the top image. Now let's look at the topography and how this is kind of impacted by the angle. Surprisingly enough, ground features, they're not really affected as much. We can see here that the scan lines are nearly 90 degrees to the curb, but a cross-section proves, there's sufficient definition. Keep in mind, this is a simple example, and there may be many cases, although rare, that this is not true. Scanner configuration is more of a craft, and with experience and research, you'll know which best fits your application. And budget. We can't forget about the budget. In summary, here's my take on what impacts topography extraction the most. So relative alignment and fuzziness of the data, densities of the data, and the intensities and their consistency usually affects the extraction process because it affects the end user as well. And things that mildly affect the output or the productivity here is subtle misalignment in the imagery, having RGB values, and then the scanner configuration itself. And remember, this is a quick list for topography extraction. It'll change for other applications. So if you notice, I put image resolution for assets as a big factor, but that's if you're locating assets and determining signs and stuff like that, and maybe those signs are at some distance from the road. You need those higher resolutions. All right, time to wrap things up. Why is all this important? Well, because assessing data maintains the integrity of the project, and it assures that the collected data will meet the project requirements. And this provides a documented lineage back to your signed and sealed data. We can also see how data characteristics impact productivity. So with an evaluation of data quality confirmed, there will be no surprises. This is ultimately going to be aiding in the improvements to productivity, lowering costs, and reducing those repeat trips to the field. All right, if you have questions, let's go ahead and talk. I'll leave you with some of our contact information. Here's a few options on how to get a hold of us. You can phone us, visit our website, or email us at info@topodot.com. And if you're into socials, find us there. Again, my name's Mike Cook, the lead applications engineer at TopoDOT. Thank you for your time.